Welcome to this new online tutorial in bioprocess engineering, digital scale-up of microbial fermentation on spreadsheet. In this tutorial, we focus on scaling up the fed batch operation mode, starting with the simulation of fed batch fermentation. In the bioprocess engineering online tutorial series, I present the core principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell culture processes. I also explain how to use spreadsheet software to carry out key bioprocess engineering tasks, including analyzing experimental data, modeling and simulating bioreactors, scaling up and optimizing processes, designing integrated bioprocesses, evaluating economic and environmental performance, and performing sensitivity and uncertainty analyses. In this tutorial series, we focus on scaling up microbial fermentations from the laboratory to the industrial fermenter, considering batch, continuous, and fed batch modes of operation. The series emphasizes digital scale-up, using mechanistic or knowledge-based models to predict process behavior across scales. These models act as digital twins, virtual representations of fermenters, enabling in silico experimentation under a wide range of operating conditions. Unlike empirical approaches, they allow virtual testing prior to implementation, reducing costly pilot trials and accelerating process development. For digital scale-up and optimization, bioprocess engineering relies on knowledge-driven simulation models, grounded in the fundamental understanding of physicochemical and biological phenomena. These models capture the key mechanisms governing microbial fermentations, including cellular reactions, fluid flow dynamics, and oxygen mass transfer. The tutorial series explains how to implement the digital scale-up approach using spreadsheets. For each of the three operating modes, batch, continuous, and fed batch, it is organized into two main steps. First, building a simulation model of the industrial fermenter, and second, using this model to optimize its operation. The modeling and scale-up methodologies for microbial fermentations are presented in separate earlier tutorials, covering microbial cell kinetics, governing phenomena of microbial fermentations, aeration scale-up in microbial fermentations, and simulation models of microbial processes. In this tutorial, the scale-up methodology is illustrated through a case study on the fermentation of baker's yeast, Saccharomyces cerevisiae, progressing from laboratory scale to an industrial 100 cubic meters fermenter. Under aerobic conditions in a glucose-containing medium, batch fermentation exhibits diacic growth. Cells first grow on glucose and then switch to the ethanol produced during fermentation. In fed batch mode, only part of the glucose is initially introduced into the fermenter, while the remainder is continuously fed to maintain a low glucose concentration. Under these sugar-limited conditions, ethanol production is strongly reduced, and yeast growth occurs primarily on glucose. In this tutorial, I present a spreadsheet-based approach to build a simulation model of yeast-fed batch fermentation in an industrial fermenter. We will examine the four sections of the spreadsheet in sequence: yeast kinetics, fermenter agitation and aeration, numerical integration table, and fermentation simulation curves. The first spreadsheet section defines the kinetics of the yeast strain Saccharomyces cerevisiae used in the process. In this section, you specify the kinetic laws and associated parameters governing yeast growth and metabolism. It also allows you to visualize how the specific rates vary with glucose concentration, particularly under the glucose-limited conditions characteristic of fed batch fermentation. For the yeast-specific growth rate, You use the classical monotype law as a function of glucose concentration. Mu equals mu max, glu divided by K glu plus glu, where mu max is the maximal specific growth rate and K glu is the half saturation constant for glucose. In this sheet, you specify these two kinetic parameters for the selected yeast strain and visualize how the growth rate varies, particularly in the low glucose concentration range. The ethanol production rate associated with growth is assumed to be proportional to the specific growth rate. The specific ethanol production rate, Qeth, is expressed as the product of the stoichiometric coefficient Yeth over x and the specific growth rate mu. The stoichiometric coefficient Yeth over x is expressed in grams of ethanol produced per gram of biomass formed. Under glucose-limited conditions, ethanol production is strongly reduced. This is described by making Yeth over x dependent on glucose concentration. It reaches a maximum at high glucose levels, fermentative metabolism, and decreases at low glucose levels, respiratory metabolism. This dependence is modeled using a sigmoidal relationship. Yeth over x equals Yeth over x max, glu to the power 4, divided by Keth plus glu to the power 4, where Yeth over x max is the maximum value at high glucose concentration, and Keth is adjusted to the threshold glucose concentration for ethanol production. For a given set of kinetic parameters, the spreadsheet allows visualization of how Yeth over x and the specific ethanol production rate, Qeth, vary with glucose concentration. The specific glucose consumption rate of the yeast includes two contributions, one associated with biomass growth and another with ethanol production. The specific glucose uptake rate, Q-glu, in gram glucose per gram biomass an hour is expressed as the sum of these two terms. Q-glu equals Y-glu over X, mu, plus Y-glu over Eth, Qeth. Here, Y-glu over X represents the glucose consumption per unit of biomass formed, and Y-glu over Eth, the glucose consumption per unit of ethanol produced. For a specified set of kinetic parameters, the spreadsheet allows visualization of how the specific glucose consumption rate varies with glucose concentration. The specific oxygen consumption rate, QO2, in gram oxygen per gram biomass an hour is assumed to be proportional to the cell growth rate. QO2 equals YO2 over X, mu. Here, YO2 over X is the stoichiometric coefficient, expressed in gram of oxygen consumed per gram of biomass produced. Under the fermentation conditions considered, dissolved oxygen is assumed not to limit growth. The spreadsheet allows visualization of how the specific oxygen consumption rate varies with glucose concentration. In summary, this first section of the spreadsheet describes how fast the yeast grows, consumes glucose and oxygen, and produces ethanol under controlled, glucose-limited conditions during fed-batch fermentation. These kinetic laws can be considered scale-independent and therefore applicable from laboratory to industrial fermenters, provided that concentrations remain homogeneous throughout the well-mixed reactors. The second section of the spreadsheet defines the agitation and aeration characteristics of the industrial fermenter. In this section, you evaluate the agitation power as a function of impeller geometry and rotational speed, the oxygen solubility as a function of the air pressure, the oxygen transfer coefficient as a function of the aeration flow rate. These characteristics depend strongly on fermenter size and geometry, and must therefore be specified for the 100 cubic meters industrial unit. The fermenter is a cylindrical vessel with a diameter of 4 meters and a working liquid height of 8 meters. This section first defines the agitation and aeration technology of the large-scale fermenter. In this case, the 100 cubic meter fermenter is equipped with 3 impellers mounted on a single shaft, 2 pitched blade impellers, 2 meters diameter, promoting axial flow, and 1 Rushton flat blade turbine, 1.6 meters diameter, promoting radial flow. Aeration is provided by a drilled hole gas dispersion system located at the bottom of the fermenter. The section then evaluates the key characteristics of the fermenter agitation and aeration. For agitation, and as a function of the input variable, the impeller stirring rate N, revolutions per minute, it first calculates the ungassed agitation power, PA, using standard engineering correlations. PA equals NP rho N to the power 3, dA to the power 5, where NP is the impeller power number, rho the medium density, N the stirring rate, and dA the impeller diameter. For example, at a stirring rate of 60 revolutions per minute, the flat blade Rushton turbine, NP equals 4, requires about 42 kilowatts. Each pitched blade impeller, NP equals 1.5, requires about 48 kilowatts, giving a total agitation power of approximately 138 kilowatts for the 3 impellers. In a second step, the aerated gassed power, PAG, is estimated. This power is reduced due to gas injection, with the reduction factor depending on the airflow rate. Assuming a PAG over PA ratio of 0.7, the total aerated power in the fermenter is about 96 kilowatts, corresponding to a volumetric agitation power, PAG over V, of 0.96 kilowatts per cubic meter. For fermenter aeration, the most commonly used criterion is the volumetric airflow rate, defined as the ratio of the inlet airflow rate, QA, to the liquid volume V. This parameter characterizes the overall intensity of aeration throughout the fermentation medium. It is typically expressed in VVM, volumes of air per volume of liquid per minute. A representative value for a large-scale fermenter is about 0.5 VVM, corresponding here to an airflow rate of 50 cubic meters per minute for a 100 cubic meter vessel. A second important aeration criterion for scale-up is the superficial gas velocity UG, defined as the airflow rate divided by the cross-sectional area A of the fermenter. It is expressed in meters per second. This parameter is critical because air is introduced at the bottom of the vessel through a sparger, and not uniformly throughout the liquid. The superficial gas velocity therefore directly reflects the intensity of gas injection and the resulting upward gas flow in the fermenter. In this case, at 0.5 VVM, the superficial gas velocity is approximately 0.07 meters per second. This section of the spreadsheet also evaluates the oxygen solubility in the fermentation medium. The oxygen solubility, O2 star, in grams per liter is calculated from the oxygen partial pressure, PO2, in the gas phase using Henry's law. O2 star equals PO2 over KO2, where KO2 is Henry's constant. In large-scale fermenters, a mean oxygen solubility is considered. As the vessel size increases, the liquid height also increases, creating a significant pressure difference between the gas inlet at the bottom and the outlet at the top. The mean oxygen partial pressure, PO2 mean, is therefore estimated as the average of the inlet and outlet oxygen partial pressures. The corresponding mean oxygen solubility, O2 star mean, is then obtained by dividing this mean partial pressure by Henry's constant. In the case of a 100 cubic meter fermenter with a liquid height of 8 meters, operating at an outlet pressure of 1.5 atmospheres, the inlet pressure is about 2.3 atmospheres. This results in a mean oxygen partial pressure of approximately 0.4 atmospheres and a mean oxygen solubility of about 14 milligrams per liter. Finally, this section of the spreadsheet specifies the oxygen transfer kinetics of the industrial fermenter. The volumetric oxygen transfer rate, JO2/3, in gram oxygen per liter per hour from the gas phase to the liquid medium is described by the classical mass transfer equation, JO2/3 equals KLA, O2 star mean minus O2L, where KLA in hour minus 1 is the volumetric oxygen transfer coefficient, equal to the product of the liquid side mass transfer coefficient KL and the specific interfacial gas liquid area A. O2 star mean is the mean oxygen solubility concentration at the gas-liquid interface. O2L is the dissolved oxygen concentration in the bulk liquid phase. The oxygen transfer coefficient KLA is estimated using a correlation as a function of the volumetric agitation power, PAG over V, and the superficial gas velocity, UG, according to KLA equals K PAG over V power alpha, UG power beta. K alpha and beta are constants selected for large-scale fermenters operating with low viscosity media. In the 100 cubic meter fermenter considered here, with a volumetric power input close to 1 kilowatt per cubic meter and a superficial gas velocity around 0.07 meters per second, the KLA is estimated to be approximately 300 hour minus 1. In summary, this part of the spreadsheet defines the agitation and aeration characteristics of the large-scale fermenter in use. It is here that you select the key operating variables, the impeller rotational speed and the air volumetric flow rate, and the corresponding agitation power, oxygen solubility, and oxygen transfer coefficient KLA are then calculated. The third spreadsheet section, the numerical integration table, solves the differential and algebraic equations, describing the time evolution of the fermentation components during the fed batch process. It uses the yeast-specific rates, along with the fermenter agitation and aeration characteristics, as determined in the two preceding sections. Constructing a fermentation simulation model involves deriving the mathematical relationships that describe the time-dependent variations in the concentrations of the different components in the medium. This modeling methodology follows the concept of the modeling triangle, which integrates material balance equations, expressing the principle of mass conservation, with thermodynamic and kinetic laws, describing the underlying physical and biochemical phenomena. In the example of yeast fermentation, the kinetic laws predict the rates of cell growth, metabolism, and oxygen transfer, while the thermodynamic law is used to calculate oxygen solubility in the medium. The concentrations of glucose, oxygen, biomass, and ethanol during the fermentation are governed by instantaneous mass balance equations that involve the four terms of inlet rate, outlet rate, reaction rate, and internal variation rate. In fed batch operation, the balances for biomass and ethanol include reaction and variation rate terms. For glucose, which is continuously fed to the fermenter, an additional inlet term is included. For oxygen, continuously supplied to the fermenter with the off gas removed, the balance also accounts for the inlet and outlet rate contributions. Together, these instantaneous balances define the set of differential and algebraic equations, describing the time evolution of concentrations throughout the fed batch fermentation. On spreadsheets, differential equations are easily integrated, whatever their mathematical complexity, using numerical methods. The numerical integration approximates the actual solution curve by a polygonal curve made of successive points and straight line segments. Let's consider the general differential equation describing the time variation of the concentration, dC over dt equals a function of C and T. The differential equation is transformed into a finite difference equation by dividing the time scale t into incremental time steps of length delta t. The derivative dC over dt is then approximated by the ratio of the concentration variation delta C to the time step delta t. And the differential equation then becomes delta C over delta T equals A, or delta C equals A delta T. The incremental concentration variation delta C is the difference between the concentrations Ct plus delta T at time t plus delta t and Ct at time t. The resulting finite difference equation is Ct plus delta t equals Ct plus At delta t. At is the slope at time t of the concentration time variation. The difference relation between the concentrations at time t and t plus delta t is used in the following way to carry out the numerical integration. The integration is started from the initial concentration C0. The slope A0 is calculated at time 0, and the concentration C1 at the following time T1 is determined by adding to C0 the concentration increment A0 delta T. At time T1, the slope A1 is then recalculated, and the concentration C2 at the following time T2 is determined as C1 plus A1 delta T. The procedure is repeated to calculate C3 and the following concentrations over the whole investigated time period. The numerical integration is readily implemented in a spreadsheet table. The columns compute the feeding flow rate and the medium volume in the fermenter, the concentrations of the different components, the yeast-specific rates. The rows represent successive time points, increasing in increments of delta t. In this case, delta t is set to 0.1 hour or 6 minutes. In the numerical integration table, the glucose feeding rate, or medium flow rate, is calculated at each time step to maintain a near steady-state glucose concentration during fed batch operation. At any given time, the glucose feed rate is set equal to the glucose consumption rate in the fermenter. This consumption rate is determined from the specific glucose uptake rate and the yeast concentration at that moment. The corresponding medium flow rate is then obtained by dividing the glucose consumption rate by the glucose concentration in the feed. The methodology for constructing the numerical integration table is described in detail in the previous tutorial, Microbial Fermentation Simulation Model on Spreadsheet. The results of the numerical integration table calculations, namely the time evolution of component concentrations during the fed batch, are displayed in the Simulation Curves section of the spreadsheet. In this section, you can specify and adjust the operating variables of the fed batch fermentation. In addition to the agitation speed N and the airflow rate QA defined in the agitation aeration section, you can set the following 5 key variables: the initial glucose concentration, GLU0, and biomass concentration, X0, the initial volume fraction, V0 over VT, the feed glucose concentration, GLU feed, and the target steady-state glucose concentration during feeding GLU-SS. For example, a typical yeast-fed batch operation may use GLU0 equals 1 gram per liter, X0 equals 0.2 grams per liter, V0 over VT equals 0.7, GLU feed equals 200 grams per liter, and GLU-SS equals 0.2 grams per liter. Under these selected operating conditions, you can visualize the dynamics of the fed batch fermentation. After an initial batch phase lasting a few hours, the following behavior is observed: a regulated constant glucose concentration around 0.2 grams per liter, an exponential increase in biomass concentration, minimal ethanol production, an exponentially increasing feed flow rate, and a gradual decrease in dissolved oxygen concentration. Moreover, you can immediately visualize how changes in the operating variables affect the fed batch dynamics. For example, increasing the steady-state glucose concentration from 0.2 to 0.4 grams per liter leads to a faster rise in yeast biomass due to a higher specific growth rate, while simultaneously promoting increased ethanol production. From the simulation curves, you can also determine when the fed batch fermentation should be stopped. A fed batch process operated at constant glucose concentration is terminated when one of the following conditions is reached. Maximum working volume. The fermenter is filled. That is, the volume fraction V over Vt reaches 1. Oxygen limitation. The dissolved oxygen concentration, O2L, drops to its minimum allowable value. The fermentation is stopped as soon as the first of these limits is encountered. The limiting condition depends on the operating variables. For example, with a feed glucose concentration of 150 grams per liter, the process is typically stopped by fermenter filling. In contrast, at a higher feed concentration of 250 grams per liter, oxygen limitation occurs first and dictates the end of the fermentation. In summary, in this tutorial, you learned a spreadsheet-based approach to building a simulation model of a yeast-fed batch fermentation. The model is developed through 4 interrelated spreadsheet sections. The first defines the kinetics of the yeast strain used. The second describes the agitation and aeration characteristics of the industrial fermenter. The third performs the numerical integration of the mass balance equations governing the fermentation dynamics. And the fourth presents the simulation curves of the fed batch process. The construction of this simulation model represents the first step in the digital scale-up of a yeast-fed batch fermentation. In a forthcoming tutorial, we will cover the second stage of the digital scale-up strategy, using the simulation model to optimize the fed batch fermentation process. If you would like to explore this further, you can deepen your understanding of spreadsheet-based simulation modeling by enrolling in one of our 2 online courses, Digital Scale-Up and Optimization of Microbial Fermentations, and Simulation, Scale-Up, and Optimal Operation of Microbial Fermentations. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.